All right, well, I think it's time to get started. So good afternoon, everyone. For those of you who don't know me by now, my name is Darrin Thome, and I'm the Associate Regional Director for USGS's Southwest region here in Sacramento. I'm glad you could all make it for our third and final workshop on wildfire science between USGS and the state of California. We understand we might have some Forest Service friends with us today, and that's great. So today's workshop is covering the topic of hydrology as it relates to wildfire management. And as I mentioned at our first two meetings, these workshops are an outcome of conversations between USGS and the California Natural Resources Agency, and they're designed to strengthen our connections between USGS science and the information needs of the state of California. So today we have 4 scientific talks, each of which will be 10 minutes of presentation followed by 10 minutes of discussion. So as always, we encourage your questions after each presentation, and we look forward to our dialogue, so don't hesitate to ask questions. So one logistical note, it'll help the bandwidth of this meeting if you all turn off your cameras unless you're presenting or asking a question, in which case we really do encourage you to turn your camera on. And with that, I'll turn it over to Loretta Moreno with the California Natural Resources Agency for a few remarks of her own.
Hi, everyone. I was going to say good morning, but it's already the afternoon. I just want to thank USGS again for this third workshop today. We're really excited to get into the material. The last 2 workshops have been really informative, and we do encourage everyone on the call today to ask questions or follow up with emails to our USGS colleagues to get what you need for your work. You know, I think this is the beginning of a long-term relationship with USGS and just to expand our work together through time. So thank you for today and for the work to come. We're really grateful to the whole USGS team. Thank you.
Thanks a lot, Loretta. Appreciate it. So before we launch into our scientific presentations, Eric Reichard, the director of our California Water Science Center, has some introductory remarks.
Hi there. And yeah, we really appreciate all the person time invested in this and the other 2 workshops. So yeah, thanks so much. So I am, as Darrin said, the center director for the California Water Science Center. So you've gotten a bit of a flavor for some of the science centers that make up the portfolio of USGS science here in the Southwest and particularly in California. So I just want to real briefly orient you to our California Water Science Center. Most of the speakers you're going to be hearing today are in our center. And just to give you a little context, the USGS has water science centers basically in every state, although some states are combined, but there's a USGS water science presence in every state. And we have a kind of a unique role as a federal agency or as a part of a federal agency in that the majority of the work we do is cooperative work with other federal agencies as well as state and local partners. And a large component of our partnerships are with state of California agencies. So we're very much attuned to serving dual missions of addressing the water data and water science needs that help the resource managers in California, but also serving the broader USGS science mission nationwide. So just wanted to show you here to orient you a little bit to how things are oriented geographically. We have office locations.
Hey, Eric, you went on mute there.
Okay, I don't know how.
Just for a moment.
I don't know how that happened. Yeah, I don't know where I started on mute, but I just want to orient you with our office locations first on the left here, and the 2 blue locations, Sacramento and San Diego, are the locations of our main project offices, and in red are the locations of our 9 field offices around the state. And I want to focus a bit on our field offices because that's where we mobilize to do our statewide long-term monitoring activities. And you can see on the right a map showing our surface water monitoring sites. I promise not to go into each dot on this, but we operate about 500 stream gauges on our own. And then we also review the records of about 500 additional gauges. Those are the dots in red you see mostly in the Sierras there. Those are mostly for FERC compliance. But to kind of give you a sense of our footprint of our surface water monitoring, we also do a long-term groundwater monitoring throughout the state. And as part of our monitoring activities, we collect information on not just flow, but we do a lot of water quality, sediment work, and we also, as I mentioned, do a lot of groundwater activities. We have our data collection, long-term monitoring side, and then the other side of our shop that Anka Mueller-Solger leads, she's on the call here, is our projects, and that's where we do our interpretive science utilizing extensive data collection. And you'll be hearing from some of our scientists from those project groups. I just want to delineate that a lot of our work relates to water quality, both groundwater and surface water. We do specific work relating to the impacts of oil and gas development on groundwater conditions. That work's done in partnership with the State Water Resources Control Board. We do a lot of work in the Bay Delta as part of several of our groups, including our hydrodynamics and sediment group and our biogeochemistry and contaminants group. That work is done in collaboration with a lot of agencies, including many state agencies, including DWR. And we also have an aquatic ecology group that works throughout the state, and that a lot of focus on the Bay Delta and the contributing watersheds. And I'll just say that our scientists speaking now are going to update you on 4 activities that are pertinent to fire issues.
Great. Thank you. Appreciate it, Eric. Yes, Michelle Stern is up next, and she's going to tell us about using the Basin Characterization Model to characterize post-fire, forest fuel treatment, and meadow restoration hydrology in a changing climate. Michelle, it's all yours.
Thank you so much. And hi, I'm really happy to be here. My name's Michelle Stern, and I'm a hydrologist with the California Water Science Center in Sacramento. So today I'm going to talk to you about characterizing post-fire, forest and fuel treatment, and meadow resilience in a changing climate with the Basin Characterization Model, or BCM. And I've worked on the BCM with Dr. Lori and Alan Flint, who are now USGS scientists emeritus for over 10 years. Next slide, please. Great, so there's a lot of data and monitoring efforts in California, as we know, including remotely sensed data like MODIS and ASO LiDAR measurements of snow water equivalent, as well as soil moisture and stream flow. There's also a great number of models used in the state, but all of these models are different and with different assumptions and purposes. So today I'll be describing a regional water balance model that has some unique capabilities to assess conditions for resource managers. Existing and ongoing monitoring and remote sensing are used to calibrate and validate the BCM. And with this model, we can forecast water supply and climate extremes, as well as analyze the range of accumulated drought conditions across the state. And the BCM has been under development since 2007, and with the support from DWR since 2010. And we're really grateful for their support and all the other partners who have helped get the BCM where it is today. And this year, we just published the BCM as a USGS code with an associated manual as well as a data release that I have links to in this presentation. And with the data release, you can download the model, a working version of the model, and run it yourselves. And you can also download our downscaled climate data at 270 meter resolution, as well as all the BCM outputs from 1896 to 2020. Next slide. So this model is based on a simple water balance calculation that includes rigorously developed energy balance and soils data, and it includes spatially distributed permeable bedrock for distributing recharge. And as I said, we downscale climate to 270 meters. And the BCM has been calibrated using hundreds of snow sensors, potential and actual evapotranspiration, and stream flow stations across the state. Next slide. So one of the BCM outputs that has garnered a lot of interest lately due to drought and wildfires is climatic water deficit. And this variable has been used to characterize species distributions, wildfire risk and fire danger, changes in irrigation demand, forest die-off, and the evolution of drought. So note in this image, the oak woodlands here seek out the deeper soils in the valleys and the north-facing slopes where climatic water deficit is the lowest. Next slide. So here's, we calculate climatic water deficit in the BCM as the annual evaporative demand that exceeds available water, and that is potential minus actual evapotranspiration. CWD, or climatic water deficit, integrates climate, energy loading, drainage, and available soil moisture storage. It addresses irrigation demand as well as defining the level of stress and wildfire risk on the landscape. We've seen that the earlier the snowmelt, the higher the annual climatic water deficit through time. And the hotter it is, the higher the potential evapotranspiration, and therefore the higher the accumulated climatic water deficit over the season. And when we accumulate CWD over multiple seasons, it can describe the loss of water from a deep unsaturated zone. Next slide. And this is what CWD looks like on the landscape on the right. So we have CWD for 2001 here. And it's pretty clear where the cooler places are in blue colors and where it's really hot and dry in red colors. And notably, you can see the north and south facing slopes on the south part of this image. This is the Bay Area, and that's due to the energy loading differential in potential evapotranspiration. Next slide. And here we can see of temperature on landscape stress for two very different droughts in California. And on the left, you see 1977, which was notoriously a year with no water. And then on the right, we see 2014, which had a similar amount of precip, right? But it was also a lot hotter. And it was many years of drought accumulating. So on the right, we have a lot more landscape stress due to temperature. Next slide. So here we can accumulate the climatic water deficit departure from baseline over water years, and then we group the values into low and medium and high climatic water deficit. So on the left, we see water year 2019 that had a few places reset after the drought in blue. But 2020 in the middle was the hottest on record at the time, and it resulted in high landscape stress with a lot of wildfires. We know that 2021 has been even hotter. So we completed a forecast through the water year using the August and September climate from 2020, which so far has been a conservative estimate. And 2021 climatic water deficit is really high across the state, and we're kind of in trouble. Next slide. And here we are zooming in on the Santa Rosa Plain and Sonoma Valley to illustrate the same methodology and correspondence to wildfire risk. Here we only go to 2020, but you can see the continued increase in climatic water deficit starting in 2014 with the peak years from 2015 on when there were big fires in this area. 2019 had a really wet winter, and with the longer and hotter dry season, the wildfire risk was elevated even further. Next slide. So switching gears a little bit to talk about how we can manage watersheds for multiple benefits like base flow. And this is an example in California in a basin that's dominated by Douglas fir, the pink color on the screen. And you can see the river drains northwest into a reservoir, and the resource managers were interested in late season flows to accommodate fisheries. Next slide. And first we calibrated stream flow to historical conditions at a gauge, and then we ran scenarios that correspond to vegetation management. And this is late season stream flow when there hasn't been any rainfall, so we know that these are base flows into July and August. And with the removal of different levels of vegetation from LAI equals 1 leaf area index, at 20% increments, you can see increases in the late season flows. So for an example, if you removed only 20% of the transpiring vegetation, say you removed most of the understory plants or maybe did a controlled burn, you could get an increase in August base flows of over 40%. And this is something we could do at any stream gauge to inform vegetation management. Next slide. And here's an example of removing vegetation as a result of wildfire. And once calibrated, this can be used to assess the likelihood of increases in peak flows following wildfire. And this example is assuming a loss of 70% of the vegetation in this Colorado 2020 wildfire, the East Fork, that burned 89,800 acres. Next slide. So we start with our calibrated model at the top, and then we can remove 70% of the vegetation within the fire boundary and rerun the model. And the reduction in 8UT leaves water in the soil, resulting in increased stream flow as the snow melts in May and June. Next slide. So here I'll briefly talk about characterizing meadows in the Sierra Nevada. This site is just south of Lake Tahoe that was recently burned and continues to burn in the Calder fire. And using a distribution of long-term standard deviation of recharge, we can identify thresholds to categorize vulnerability of meadows through time. Next slide. Meadows that have little change over time are categorized as low vulnerability in green here, average in yellow, or high vulnerability in red. And we can see that less historical variability can result in meadows that are more resilient to change. Next slide. So using climatic water deficit, we can find meadows that are stable over time and thus more resilient to change. And meadows with low recharge and climatic water deficit vulnerability could be prioritized for restoration or protection. And this analysis was done using the 270-meter publicly available data set for the statewide BCM. But as you can see from the zoomed in window on the right, a finer scale model might be more suitable for characterizing meadows at this scale. Next slide. So conclusions, regional modeling tools can be useful in characterizing the landscape conditions that lead to wildfire. The BCM can be used to provide information for prioritization of management strategies. Sensitivity analyses and scenario testing, including future climate scenarios, can provide additional information for resource management. And finally, characterization of hydrologic processes at a fine scale supports decisions about forest and meadow management. Next slide. So here I've just put up some links and references and the Basin Characterization Model website for your reference and my email. So with that, I'll take any questions.
Yeah, Michelle, thank you so much. That's a very powerful tool. So if anyone has questions, please either just raise your hand or enter your question into the chat, and yeah, we'll talk. Just got a question for Michelle. I've got questions I can ask, but I want to make sure that we give our partners a chance. Let me get the ball rolling. No, it looks like there's a couple here. Let's start with Loretta Moreno.
Michelle, thank you for that presentation. I have a question about the data you have for wetland meadows. You were mentioning the resolution of that data. Are you finding that to be useful? Do you have concerns around its limitations for your assessment? Like, would you have any improvements you would think are needed for planning, or do you think it's a pretty sufficient resolution?
I think it's a thanks for that. I think it's a good first pass to kind of get a general idea for the whole state. But then as we're going to talk a little bit more about meadows with Judy Drexler and Matt Brooks in the next talk, so I won't get too much into it. But I think we all agree that a finer scale model would do a better job at characterizing these really small meadows footprints. And that's something that we plan on doing, hopefully, but it's in the works still. I think that, you know, if you're looking at all the meadows in California, it's harder to do a really fine scale model. But when you can focus in on specific meadows or areas, it makes it a lot more reasonable and probably more accurate too.
Thank you. I have one little other question, and this is something that maybe you don't have to answer right now, but I would like to understand if there's any sort of data gaps, probably for you and all the speakers today, any kind of data gaps that you feel are, could be met and filled and then help support your work. I ask because we have some remote sensing funding at CNRA that we're, looking to allocate for different purposes. And it would be interesting to know if there's anything in your space where, maybe we could consider filling gaps for your work.
Yeah, that's a great question. I have a lot of ideas about that, but I'll just say that I think soil moisture is one area that we have a pretty big data gap that might be able to be filled with more monitoring and remote sensing, as well as evapotranspiration, just to name a couple. So we should definitely talk more about that.
Thanks for the question, Loretta, and we'll see if we can put pen to paper on some of these gaps to send to you shortly after this too. So the next question looks like is from Shangli Huang. Is that how you pronounce it?
Yeah. I'm from U.S. Forest Service. I have two questions here. The first question is, you show we have a lot of surface water monitoring sites. Is the data available to public, or how can we get this data for calibration or validation?
Yeah, so all the stations that we used were NWIS stations available online. I can throw the link into the chat. I'm sure you're aware of that data set, and that's what we mainly use to calibrate the stream flow here. But all of the recharge and runoff and the outputs of the BCM are available online in one of the links that I shared.
So those data are for public access, right?
Yes, publicly available.
Okay.
Yeah.
The second question about your model, the leaf area index is one of the model input. So let's say we do some forest management and leaf area index will change in the next, for example, 50 years or 100 years, etc. So can you do any water projection? I mean, not current. Current, I know you remove some vegetation, they change the LAI, then the water change. But after management, LAI change for a long time, every year, for 50 years or 80 years or 100 years. Can you model this projection, water projection?
Well, we can. So we can set an initial LAI. It's a parameter value, so we can calibrate to data. And we do have parameters in the model that can allow vegetation to grow back, and you can set the rate at which it grows back, and then eventually it will come back up to the full LAI value unless you change that. So yeah, there's different ways to do that, and that's something that we would love to get more data to calibrate to.
Okay, that's great. That's my question, because I project LAI for many years. I'm thinking how to use this data to improve water modeling. So perhaps we can talk about this later. Thank you so much.
That would be great. Thank you.
Thanks for the question. Who else has got a question? Feel free to raise your hand or enter it into the chat. Jim Falter.
Yeah, hi, thanks for the talk, Michelle. I was just curious, to what extent do you think temperature versus vapor pressure deficit are driving the climate water deficit? I mean, I know they're correlated, but they're not exactly the same. Do you have any thoughts about that?
They are correlated, you're right, and we don't explicitly model vapor pressure deficit, but that is something that we could incorporate. I know that Alan and Lori are on the call. Alan, do you have anything to say about that?
Come on. Yeah. Oh, yes. The biggest part is that we used all of the stations in the Western U.S. to estimate potential evapotranspiration. We did that for about 15 years worth of data, and that takes into account, those are calculated like using the Penman-Monteith equation. So they take all of that into account with the measurements they do. And once we have a calibrated model, then we use changes in air temperature to change the potential evapotranspiration. And so everything is based on a fairly large data set from ET stations across the California, Arizona, Nevada. And then the actual evapotranspiration is calculated in the model, and it's calibrated to a regional actual ET model that was based on a water balance, ET, groundwater measurements. It was done by the USGS out of Reston, Virginia. So it's a pretty rigorous data set. So the PET is good, we think, and then the AET is calibrated to another measurement data set. So it accounts for those parameters.
Sounds good. Thanks for the explanation.
Thanks for the question. Who else has got a question or a comment for Michelle? I've got one for you. Michelle, how difficult would it be to integrate a fuels map with climatic water deficit mapping? And is that something that's been done?
That is something that's currently being worked on too. Yeah, that's in the works as well. We're working with multiple groups who are looking at wildfire risk and fuels, and so some of the BCM layers are being used in those models as well. But
so, okay, and are you using BCM to optimize landscape treatments to consider, forest health, fuels buildup, stream flow, to determine where these treatments can be located on the landscape?
Yeah, I think, well, Lori can correct me if I'm wrong, but I believe we have done that in a few locations. Is that right?
We've done a lot of, we haven't done it with specific data sets. We have done a lot of calibration to stream gauges with different amounts of vegetation on them. We have also done a lot of scenario testing, removing different amounts of vegetation depending on where they are and seeing where the management would get the most bang for the buck in terms of increasing the hydrologic response.
Thanks, Lorraine. Michelle, thank you very much for a highly educational talk. Appreciate the discussion as well.
Thanks for having me.
Okay, we'll shift gears. We're going to be talking about meadows, and Matt Brooks with the Western Ecological Research Center and Judy Drexler with the California Water Science Center are going to be talking about meadow vulnerability in relation to climate change. So, Matt, I think you're going first.
Yep, thank you very much. In this presentation, Judy and I will be describing our work evaluating vulnerability of Sierra Nevada meadows to a changing climate. I'll describe my work, which has been focused on utilizing satellite imagery, 30-meter data for the most part, to establish vulnerability of the 8,000 plus meadows in the Sierra Nevada network, Yosemite, Sequoia, Kings Canyon, and Devil's Postpile. Judy will then describe her work using aerial photography and hydrologic modeling, and she'll conclude talking about some of the plans where we have to combine our approaches in terms of evaluating meadow vulnerability in the Sierra Nevadas. Next slide. So I'll just preface this by saying that meadows are iconic features, highly valued for their watershed functions, wildlife habitat, recreational opportunities. One of the reasons why the work I've been doing with the Park Service, in particular the Park Service, wants exceptional degree of precision about information about meadows to help manage them. Next slide. Meadows include a lot of different hydrogeomorphic types. They range from merges or the verges of lakes, those that have streams to them, peatlands, dry upland meadows, and they all range quite a bit in terms of their potential vulnerability to exposure to threats, sensitivity to change, and their adaptive capacity. Next slide. In terms of exposure to threats, major threat to meadows, especially since they're so fundamentally tied to hydrology, is climate change, especially as we're experiencing warmer summers, warmer winters, earlier springs, longer summers. And associated with those changes are altered fire regimes, in particular in the watersheds around the meadows, non-native species, land uses such as pack stock, and contaminants such as nitrogen deposition. Sensitivity to change, the things in particular are transformation from one meadow type to another. That's has been documented within historical records, and there's concern that that might be happening at an accelerated rate. And in particular, how this affects things such as habitat for the Yosemite toad, which requires meadows for breeding. And then the adaptive capacity related to resistance and resilience of meadows to change. There's quite a range of meadows, some of them less than 10,000 years old since the last ice age, And they've changed quite a bit even in the last 100 years. Some of them haven't changed much. So there's indications that meadows vary quite a bit in their potential adaptive capacity. Next slide. So what my group's been working on is focusing on evaluating all the meadows in the Sierra Nevada networks and using Landsat data from 1986 to present. We've derived normal differenced water wetness indices, the NDWI, to evaluate moisture stress as an indicator of drought. Variation in NDWI wetness, we specifically looked within year from the beginning of the summer to the end of the summer, and among year variation as an indicator of hydrologic regime, whether it's a groundwater derived or surface runoff derived hydrologic regime meadow. Next slide, please. So this is a plot showing two meadows in Yosemite. The blue-green plot is a meadow that dries from the left side in June down to the right side in September. The y-axis is the NDWI average values, or I should say the NDWI value over the data set we have since 1986. And the y-axis is the day of summer, basically from June to September. So some meadows dry down during the summer. Some meadows, like this fuchsia colored one, remain relatively constantly wet throughout the summer. Click, please. These wet ones that have high within year variation suggest a surface runoff regime, which we're inferring as being more vulnerable to threats, especially early springs and drier late summers. Next slide. And then these orange ones that have lower within year variation, we're referring as having more of a groundwater regime that we think is more buffered to change. These meadows may be less vulnerable to threats. Next slide. And so what are we doing right now is we're finishing a series of years where we're monitoring wells to determine if these groundwater wells are corroborating what we're seeing in the remote sensing. And so we're basically validating our remote sensing. And the next steps are to potentially extend this this approach to other meadows in the Sierra Nevada within California. And then also in some collaborations with Judy, potentially, and some others like Michelle, we have been talking about evaluating mechanisms, mitigation strategies for specific threats, and particularly altered fire regimes. And now Judy will pick that discussion up from here.
Thank you, Matt. Yeah, so I want to drill down a little deeper in how we can use montane meadows as a window or even a gauge into the hydrologic function of a watershed. Here we're looking at Drexler Fen in Yosemite. It occurs at a break-in slope where the groundwater meets the land surface. And these wet meadows exist throughout California. They aren't as common as some of the other drier meadows that rely at least partially on snowpack and, as Matt said, are sensitive to faster and earlier melt. Meadows do a lot of biogeochemical functions, such as transforming and storing nutrients. They could also end up storing contaminants and sediments, and they can function as a carbon sink. And you can see the picture of the beautiful, nice peat from Drexler Fen. Drought, climate change, and likely fire due to greater runoff and sublimation rates after fire are decreasing meadow extent. But here's where there's a real data gap. There's very few data available on this. And this makes it difficult to choose the most sustainable sites for restoration and also to maintain and manage sites for sensitive species. Next slide, please. So I'd like to go into a little bit about a previous research project I did with Lori and Ellen Flint and Donna Nifong, where we analyzed 7 wet meadows. 5 of those were in the Sierra and 2 were in the Southern Cascade Range. And what we really did was use these as ecosystem gauges. I looked at the aerial photographs going back in these sites, and the reason we have such few sites is because these sites didn't have any other disturbance except for climate change. And I delineated the wet meadow part so you could see these brown mosses from the air very clearly, and you can see the area that they occupy in these fens. And so I delineated these going in photos from 1940 to about 2010. And then the Flints helped me with the climate analysis, where we looked at monthly snow water equivalent values for the last 70 years, and also, of course, the Basin Characterization Model, where we looked at minimum temperature, precipitation, and snow water equivalent. Next slide, please. So we had some really interesting results from this project. You don't have to look at each of these plots, but the plots on the y-axis is the delineated area in meters squared, and the x-axis in is time. And these are all across the state, as you saw on the previous map. And the really interesting thing is that the decrease in delineated area in these wet meadows was all between 10 and 16%. And this is a subtle change, but it is definitely a change. And we tied this to changes in recharge. And recharge occurs in the mountainous west mainly under snowpack. So the fact that there's decrease in the delineated areas show us that there was decrease in recharge. Next slide, please. So, and here's the climate analysis. We compared 1951 to 1980 and 1981 to 2010, and we saw increases in temperature, and we saw declines in April 1st snow water equivalent, and significant changes in June months with no snowpack. And all of the Sierra sites had this again. So this is showing that there's likely a long-term decrease in recharge. Next slide, please. So clearly, long-term analysis of meadows can be very useful in understanding hydrologic changes that result from climate change, and could also be used to look at fire and drought. So we propose a Sierra Meadow monitoring network focused on hydrology, which could have a stratified system where you look at a lot, maybe hundreds or even thousands of meadows using remote sensing, and then you kind of hone in on some indicator meadows that's much fewer but well spaced throughout the Sierra for ground truthing. We have a number of tools that we could use. We could use the remote sensing approaches that Matt described earlier. We could use the well data to do the verification on the landscape. We could use the aerial photo analysis that I just described to assess long-term changes in meadow habitat, which could inform restoration actions and also help us understand how the critical habitats that we have to manage are doing. And last but not least, we can use models such as the Basin Characterization Model to project where meadows and their watersheds will be resilient to future drought, fire, and climate change. And I think that's my time, so I'm going to stop there, and we'll be happy to answer any questions. And thank you for having us participate this afternoon.
Nice job, Matt and Judy. Appreciate it. Yeah, we'll open it up for questions. Again, feel free to raise your hand or enter a question in the chat. And I'm really curious from the state perspective, does the state have management concerns regarding meadow sustainability? And you know, what from the state's view are the threats to some of these meadows? Any thoughts on that, or any questions in general for Matt and Judy? Loretta.
Hi, thank you for that presentation to both of you. I am sure others on the call could speak more specifically about management concerns in meadows. I can just relay that through various public workshops as we're working to establish our kind of statewide integrated monitoring for forested systems. Wetland meadows continuously come up as a broad concern shared by not only our scientific community, but the general public, NGOs, and so forth. So it is a priority topic. And I think, you know, Darrin, you know that the state's working on that integrated planning effort, and meadows will be a topic of focus as a part of our assessment. So it's just, yeah, very important. I do have a question. There was a reference to considerations that I don't think you got into it in the presentation, but around the selection of wetland meadows for priority restoration. And, you know, I'm wondering what considerations come into play as far as how you select a viable site, given the climate factors at play. Like, do you have any kind of spatially explicit decision-making analytics that go into that, where you make those decisions, or is it just this data is then used to just kind of flag areas of concern? I mean, where are you taking that analysis, I guess?
I can provide an example. One of the ways we're applying it is to identify refugia habitat for Yosemite toad. So we have a niche model for the Yosemite toad habitat, breeding habitat, and we've applied that niche model as an overlay on our vulnerability, hydrologic vulnerability assessment, so we can try to find habitats that are high value habitats, as well as potentially those meadows that tend to stay wet during the summer. So the ones that we are inferring as being more resistant to change, maybe initially, to the warming climate. So that's one of the reasons, that's one of the ways we're applying it for specifically that species. Restoration wise, you know, the potential for a meadow, if you're going to put a lot of money into it, to be in a landscape position, to have a soil profiles that might be more resistant and resilient, probably be a good idea to put your money in those situations and those that might change due to climate anyways. And so there have been some discussions about that as well, but there hasn't been anything explicit on terms of a decision-making tool in that regard.
Okay, so you have something sort of to identify sort of passive conservation areas, if you will, that are kind of robust because they adequately, you know, they have adequate water supply. And then for areas that are more resilient in profile, those areas could be priority areas. But where areas need management intervention, that's kind of another step in the process that isn't actively part of what you're looking at.
Yes, it's another bit of information. The idea is that the vulnerability, the wetness variability vulnerability assessment we're creating for the Park Service Meadows can be used along with other data layers to make those decisions. Okay. So it stands alone, but it also can be used with other data layers like the toad niche model, for example.
That's great. Thank you.
Good questions, Loretta. Appreciate it. Who else has got a question or comment? I'll prime the pump a little bit here. So, you know, you mentioned that maybe some of the next steps are identifying strategies for reducing meadow risk. What are some of those possible strategies, and how would you evaluate them?
You want to take that, Judy?
Well, when I look at risk, I look at, you know, if we're going to spend a lot of money, we need to choose meadows to restore that are going to be there in the future. So really, a lot of what we're trying to understand is meadow sustainability, and wetland sustainability is something I've studied for many years. And of course, there's many facets to it, but the hydrology is really key. And I think it would really behoove us to really look at all the different hydrologic factors and really try to understand how they relate to vulnerability. We've talked about climatic water deficit. We're talking about recharge is a lot harder to understand and really needs to have some data. So we really need to understand, you know, like which sites are receiving even a little groundwater. You know, a lot of first of all, there isn't a lot of data on this, but even if there is, very few people go into the groundwater. We really need to get on the landscape and look at some of these measurements and see, you know, what's supporting these sites, what kind of groundwater flow systems are those, like, are they very localized? Those can dry up. Are they regional or intermediate? Those are have much more staying power. So I think we really need some, you know, so this kind of network that we're talking about could be really instrumental in better understanding what a meadow needs to be sustainable. But while we're doing that, we can even understand a lot more about how hydrology is changing in the Sierra.
Thanks, Judy. Any other questions? I've got a follow-up, but I don't want to hog it all.
Yeah, I have one. This is Michael Parker. I'm from the Central Valley Water Board, Reading, and thank you for your talk. It's very interesting. In regards to post-fire and, you know, the higher elevation meadows, are you guys planning on looking at the loss of the conifers from wildfire, so conifer encroachment into these meadows, and taking that into consideration in regards to how taking away that conifer encroachment in the after a fire comes through and the impacts to the hydrology?
Yeah, I can address that real quickly. We have been discussing those next steps of taking fire history data, crossing it with the remote sensing data of the 8,000 plus meadows we have, and determining if we see signals and changes in that wetness profile, wetness variation profile. There's some predictions that you might expect to occur with things like a wildfire in the basin or a wildfire through the meadow itself. That would really address some of that conifer encroachment. If you remove some of those woody species, do you see a change? And a lot of those things would allow us to determine, are these signatures we think are indicators of resilience occurring or displaying themselves when major factors like fire comes through in the watershed, fire comes through and maybe removes some of those woody species. There should be a change hydrologically, unless they really are, like the groundwater derived meadows, heavily buffered from those changes. So there's a lot that we can do with the data that we have, and the next steps are that we've been discussing, as I mentioned, Judy, Michelle, Lori, and I, about looking at some of those questions.
Also, with the encroachment of conifers, that could be a really helpful thing in aerial photos to understand sites that are really drying out. So if you look at, 5 years difference and you see a lot more encroachment, that's really a key. That's like a flag to that. We better really be looking more at this site and how it's changing.
Yeah, thank you for that. Yeah, because I know, certain industries, they do target in some of their vegetation management to thin out conifer encroachment. And, with these fires moving higher elevations, it's kind of doing the job for us. But yeah, so thank you.
So Eric Reichard with maybe the last question here.
Just really quick for Judy or Matt. You talk about the monitoring network and kind of ground truthing the information from remote sensing with a network, but how do you quickly go to kind of making use of that ground truthing data to apply broadly, given decisions need to be made soon and some decisions need to be made kind of urgently. So what do you recommend for approach for efficiently taking advantage of the network that you have, or strategically adding additional data so that you can make decisions for all these meadows?
Yeah. Eric, it's hard to hear you for some reason, but I think the question you're asking is how can we make use of our existing information to prioritize what needs to be done with meadows?
Judy, you want to take that?
Yeah, I mean, we're going to have a lot of like just what I was talking about at the end. We're going to have a lot of remote sense data, and say that's wetness, and we have that, and we want to be able to know that that's really what's happening on the ground. So, we can take that, we can use that as a vulnerability assessment tool, but we really need the water table measurements from the sites, and that can be done right away. I mean, that's what Matt has been collecting. So we just need to do it in a formal way, and we need to kind of have some kind of stratified system where we can go out, and what we're seeing with remote sensing, we could just check to make sure that's really happening on the landscape. And like, for instance, with the BCM, we can help, provide more inputs and improve the model, the more data that we have. So I think that that's kind of the strategy we'd like to take. There's certain things that are going to take more time to maybe improve and work out, but initial, wetness, that could be something we can do right away.
Thank you, Judy. Thank you, Matt. Appreciate this robust discussion. We do have to shift gears on to the next talk. So Charlie Alpers is going to talk to us about assessing and forecasting impacts of wildfires on environmental water quality. Charlie, it's all yours.
Thank you, Darrin. I appreciate this opportunity. Next slide, please. So it's pretty well known that forests have a lot of infiltration and relatively little overland flow, and you get the seepage into streams, and the forest kind of acts as a filter and a sponge without fire. But next click, please. In post-fire, with the vegetation missing, there's less interception of the water by the vegetation, and there can be decreased infiltration because of hydrophobic soils can develop, and so you tend to get more runoff and overland flow, which can cause erosion of ash and soils, and quicker movement of water to streams and less groundwater storage. Next, please. And then what does this mean for water quality? Well, all that ash and sediment debris being transported to streams obviously will increase turbidity in the short term, and there's documented cases of increased nutrients such as forms of nitrogen and phosphorus and organic carbon, and sometimes metals in the surface water, especially if there's mine sites involved in the fire and the erosion affecting mine sites. That can affect metals, and as we'll see a little later, when you get to the wildland-urban interface, there can be metals introduced from the built environment. All this sediment can accumulate in reservoirs and lead to sedimentation and filling in of reservoirs, losing capacity, and the eutrophication can happen in reservoirs and in streams from all these extra nutrients. The nitrate and the phosphate in particular can be critical nutrients, and that can lead to potentially harmful algal blooms. And then the transport of phosphorus into a reservoir can later be mobilized by anoxic conditions and then recirculated years later in a reservoir. So this fire effects may not be seen in the very first year. It can be later. And downstream, you can have impairments on water treatment efficiency. The sediment can be a big problem for some pretreatment systems, and the dissolved organic carbon can lead to disinfection byproducts. That'll be discussed a little bit in our next speaker. Tamara Kraus will discuss the water treatment aspects and disinfection byproducts. Next, please. So how is USGS addressing water quality effects from fire? We have work going on at different scales. On a national scale, there's a new USGS project in our water mission area, and it's got kind of a difficult to pronounce acronym. WAEE is the Water Availability Impacts of Extreme Events. It's being headed up by Sheila Murphy, who's a fire expert out of our Boulder, Colorado office. And they are looking at not just fire, but also hurricanes in the short term. They're looking at how these extreme events can impact water availability. And that in USGS, we consider water availability to include both water quantity and quality. But water quality is a crucial part of this effort. And there's an effort to come up with a national model for water availability that will include stream flow, predictions and forecasting, as well as water quality forecasting. That's all in the works with models that have not yet been developed, but it's a long-term plan over the next 4 or 5 years to develop this sort of national scale models, starting out in some key basins where that'll be calibrated. On a regional basis, this national program is providing funding to us here in California to monitor 4 locations that were affected by 2020 fires, and I'll show a map in the next couple slides. And we're looking where we can compare pre and post fire water quality. And this is a regional study where the 4 sites in California will be compared with 4 sites in Oregon and 1 site in Colorado where we're doing consistent measurements. There's also in situ water quality from sondes that are being installed in these streams. And we have a few other studies where we've done detailed investigations of post-fire water quality in Colorado, New Mexico, and some of you may be familiar with the paper on the station fire in Southern California by Carmen Burton and others out of our San Diego office. I've personally been involved in some investigations of post-fire water quality, starting in 2015 and later in the 2018 wildfires. They both affected Cache Creek, an area where we've been monitoring mercury in collaboration with California GWR. And fires greatly affected that watershed. And I'll show us, again, a couple slides about that as we go forward. And we've been looking at the effect of the fire on mercury and other trace metals in the soils and the ash in the watershed and how that affects what's suspended and transported in the stream. And the 2019 and 2020 wildfires, we've been doing some post-fire sampling with a focus more on nutrients. Again, the sites I mentioned above that are funded through this regional USGS study, the focus is mostly on nutrients. The Bureau of Reclamation has given us some funding to look at fire retardant impacts, particularly PhosCheck, which is an ammonium phosphate bearing fire retardant. There's questions about whether that has impacts on water quality and is maybe contributing to this nutrient load after fire. It's an unanswered question, but we're starting to address that and eventually trying to model that with the Bureau of Reclamation as a collaborative effort. Next slide, please. So this is a map just showing those 9 locations that the USGS regional program is monitoring. It looks like 3 black dots in California, but 2 of them are very close together. And next, please. Click. There's a close-up of the 2020 California wildfires that you're probably too familiar with by now. And one more click, and you'll see the 3 fire areas that we're focused on for this monitoring effort. There's 2 sites in the LNU Lightning Complex area that are tributaries to Lake Berryessa, 1 in the SCU Lightning, and one more click, and 1 in the Southern California area adjacent to the Bobcat fire. And a little more detail about these sites here on the left. Pope and Maxwell Creeks are the sites we're monitoring above Lake Berryessa. Arroyo Hondo is a site where we already had a stream gauge funded by San Francisco Public Utilities Group that were added more constituents and more in situ probes to. I think we were already monitoring flow and turbidity there, and we've added to that. And then in the Bobcat fire, there's a sedimentation issue in the Little Rock Reservoir downstream that Los Angeles County had been investigating, and this additional data will be of use to them as well as to our regional study. At each of these sites, we're installed in situ sonde and XO2 that has the parameters you see there. The fluorescent dissolved organic matter is a proxy for organic carbon. We're putting in ISCO autosampler so we can try to collect rising limb, peak, and falling limb flows. And then the water quality sampling, the constituents are shown there, again, focusing on the nutrients, both filtered and unfiltered, as well as major anions and cations, and some suspended sediment with the sand break so we can get some idea of grain size. We're doing oxygen hydrogen isotopes for possible hydrograph separation later, the DOC, and the dissolved organic matter quality. I'm not going to talk about that anymore, but again, Tamara Kraus in the next presentation will talk about the EAM spectra, excitation emission matrix that gives you some fingerprinting for where the organic matter comes from. And this could be very interesting as far as seeing the fire signal. Next, please. So how do we model fire effects on water quality and constituent loads that might potentially increase, such as nutrient loads or sediment loads after a fire? We're focusing on areas that have sufficient data for model calibration, and that requires having some pre-fire data. And as we'll see, that's a pretty critical data gap in many cases. You also need a continuous flow record, and our network of stream gauges is great for that, but we don't have stream gauges everywhere, and sometimes they're not in the places you want them to be. And so there may be something to think about as far as improving the stream gauge networks so they can be available for pre and post fire monitoring and modeling. The climate data is essential for these types of models. Michelle Stern mentioned how rainfall and air temperature and potential evapotranspiration and actual evapotranspiration are all used in this modeling. The leaf area index is also important, and that factors into the changes that fire brings, obviously decreasing the leaf area index and removing vegetation that affects the PET. And so some of these parameters, such as the rainfall, we need to get at a 1 hour time step to fuel the models, which we have pretty flashy streams. Daily time step really doesn't work very well. And so there's a fair amount of data calculations to get the data interpolated and gridded onto an area that you're modeling to get that time step. A couple of models that we've applied to pre and post fire conditions are shown here. HSPF is a model that's been around for a couple of decades, developed initially by USGS in collaboration with EPA. And I've worked with Michelle to apply that to the Cache Creek watershed. And then PF Hydro, a new model developed by the Bureau of Reclamation in collaboration with myself, Michelle, and Lori and Alan Flint. The PF in PF Hydro stands for post-fire. By coincidence, HSPF, the PF is not for post-fire. That's for Hydrologic Simulation Program, Fortran. But PF Hydro is a post-fire model intended to give managers a tool for trying to get a rapid assessment of what the impact might be on their watershed and their, in the case of the Bureau of Reclamation, what's coming into their reservoirs, looking at sediment transport. And then by adding the concentration of mercury to the particles in these models, and also the concentrations of nutrients such as the nitrogen and phosphorus, we can simulate the particulate transport of those constituents and how they change after fire. Mercury is known to vaporize during the fire, so the soils have lower mercury often in the highly severely burned areas. And similarly, phosphorus can increase after fire, whereas the nitrogen will decrease, and it tends to volatilize.
Hey, Charlie, just letting you know you've got about a minute left.
Okay, next, please. And this is the Cache Creek watershed where we did that, applied that PF hydro model shown in the purple area in relation to the Rocky Fire from 2015. Next, please. And then we had pre-fire water sampling a little bit in 2015, again, through the DWR's funding through the Cache Creek project, and we had quite a bit of post-fire data to compare that to. We saw how mercury decreased on the particles because of that volatilization effect, and then it recovered in 2017, and all that was used to calibrate the model for Cache Creek. And next, please. And then just, again, the wildland-urban interface. Here's an example of a burned car, one of tens of thousands of vehicles that were burned in the Camp Fire and in Paradise, tragically up in Butte County. And there's a number of metals that could be transported to the environment, such as the lead, aluminum, copper, and zinc from the tires and so forth. So the next click, please. There's a number of other water quality constituents in the urban environment, including organics, that can be looked at. And we have an ongoing study with several academic researchers, including Jack Webster, who supplied this photo at Chico State, and that's an ongoing area of investigation. But a lot more could be done on the wildland urban interface. Okay, my last slide is next. Just some concluding remarks that I've already talked about, the different scales that we're looking at. The physical and chemical processes can be simulated with the models that exist and a new model that's being developed by USGS on a national scale. But the major challenge is really comes down to finding places to calibrate these models with pre and post fire data. And it's a couple ideas about how to get pre-fire data would be to focus on some prescribed burned areas where you know the burn's coming. You can monitor beforehand and afterwards in a more organized manner. Those tend to be only low and moderate burn severity by design. And then the strategy for getting high burn severity areas, maybe we need to start thinking about monitoring areas that haven't burned yet but have a high probability of future fire, establish some sort of control sites that aren't burned, but with the idea that if we have several of those, that over time some of them will burn and we'll get pre and post fire data to calibrate models of this kind. So I'll stop there and be happy to answer any questions.
Thanks, Charlie. I know there's so much data we could be talking about. It's 10 minutes is such a short amount of time, but thanks for squeezing it in.
Yeah, sorry to go over.
You're good. You know, Loretta made a comment in the chat that we could probably talk about offline to some extent, but it's regarding what are the data gaps with respect to our stream gauges. Do you have thoughts off the top of your head on some of our larger gaps with respect to the gauging?
Yeah, well, for example, you might be surprised to know there's no stream gauge right upstream of Folsom Lake on either the North Fork of the American or the South Fork of the American. And you'd think the Bureau of Reclamation would need that to understand water management, but they can get by with the models they have, and they're technically challenging areas to put in stream gauges. You know, we need to have a bridge or a fairly expensive cableway. That's always been a barrier to getting. We need to have access at high flow. So if bridges are available, they have to be wide enough that you can work on them with the traffic. You know, it's a lot of challenges to getting good access to high flow in particular. And cableways are expensive, but that's the way you have to go. They're bank operated ones that are a little you know, possible to use. So there's a number of ways to do that, but I think focusing on sort of some of the major rivers in the Sierra Nevada where you know, by most projections, everything's going to burn eventually. It's a question of when. Really, realistically, over time, it's a natural process, and you know, because of fire suppression, there hasn't been as much burning in the last century. But I understand that there's many watersheds in the Sierra Nevada are at a high risk for burning. Not, you know, obviously with the climate change. So I think a network of stream gauges and monitoring at several key streams in the Sierra would be a good choice. And obviously, there's other parts of California that are important as well. Southern California, the Coast Ranges come to mind.
Thanks, Charlie. And we'll let Loretta verbalize maybe another question she's got.
Thank you. So actually, while we're still on the topic of the stream gauges, and we can take this offline, Charles, but I would be really interested to get a kind of a sense of the extent of gaps, like, or maybe where your high priority gaps are, which you started to talk about here, about some areas in the Sierra where we just clearly have holes in the information, and also other parts of the state. It'd be nice to assemble that to get a sense of, and also I don't know if you've done any analysis or if how hard it would be to kind of get at this question of accessibility for the gauges, like, you know, what kind of cost and extent are we talking about? Also the maintenance around it. It matters for us too, because if these are major data, I've heard this is a major data gap already, so I don't want to miss the opportunity where we could maybe coordinate resources. And then, so let's talk about that later if possible. And one other question, you mentioned this WUI analysis, you know, you were getting at sort of the contaminants from man-made materials and so forth. Can you describe a little bit more what sort of analysis and study you have going on? I ask because I know independent of water quality, the Air Resources Board is trying to get a better handle on these contaminants for other applications in terms of air quality. So what is going on there?
I was very interested to see the Air Board's recent report about the smoke from the campfire having higher metals than other fires around the same time that didn't have as much urban influence. So that's very important data. I'm working collaboratively with Jack Webster at Chico State, and we have a couple hundred water samples that were taken after the campfire collectively with himself and his students, and there's a student at the University of Colorado actually analyzing the data. And they did some of the analyses. So they're focusing on certain trace metals. There was an ash study by Tetra Tech that was done, I think, for Butte County or for the state. I'm not sure who paid for it, but we're sort of looking at certain metals, such as in this case lead and zinc and chromium, that seem to maybe have an urban influence. But it's kind of, you know, the study is in its sort of data analysis stage, and we don't have our conclusions yet, but we're looking. We have some pre-fire data, but not enough ever, and so it's just kind of using what's available to try to understand the fire effect. And we did sample a control watershed that did not burn. I think it was Little Chico Creek and several smaller creeks that did have a lot of burning, Dry Creek and Clear Creek and so forth. So I'd be happy to talk about that offline with people and give more information. The organic part is being headed by a scientist up in Tacoma named Ecological, or Ecological, I believe you pronounce it. And so he has quite a bit of information about organics. I'm less involved in that part of it myself, so I can't really speak to what they found. But I believe the PAHs are one thing that did show up. And I know the state did some monitoring funded through the Water Board, and they probably have better information on the immediate runoff right after the fire. We're focusing on samples that were taken throughout the season, the following wet season.
Thanks, Charlie. And Loretta, we'll see if we can get you some bullets on our gaps as far as gauging in the Sierras and elsewhere.
Thank you.
Bill, yeah, sure. Bill Short, you've got the next question.
Yeah, howdy, Bill Short here with California Geological Surveillance. Just following up more of a comment on Loretta's info, or Loretta's question and the comments about gaps in stream gauging. In case people don't know, there is a multi-agency group, water boards, DWR, Fish and Wildlife, and DOC CGS, looking at gauge gap for stream gauges across the state as part of SB 19. Mark Dickman is on our consult committee for that. Our charge is to determine where gauges need to be upgraded as well as placed, as well as prioritize those locations in an effort to hopefully get funding for upgrading those gauges and funding their long-term operation as well as modernizing them all. So I would suggest Mark Dickman from the USGS for all USGS contacts. I was just on to our conference call with him about this modernization piece. So, and also, if you have info, please get it to Mark so he can pass it on to us. We do have a public website. If you look at, if you Google SB19 and gauge gap, you'll go to a water resources control website. It talks about what we're doing. Our deadline is next June 30th for coming up with a plan. And we ask that people provide us information on that website, so as well as ask questions. So that's my contribution to that. And just so you know, I am the DOC rep, so I'm one of the 4 key folks on our committee doing this work, although it is led by DWR and the water boards. That's it.
Maybe I could just make a quick comment on that. I hadn't heard of that effort. It's nice to know about it. And I'll be in touch with Mark. Maybe he can bring to the group the idea of adding some probes such as turbidity sensors and other things like I mentioned, the fluorescent dissolved organic matter perhaps, or conductance, very simple types of measurements that can be very valuable for gathering that continuous data for water that can be proxies for other water quality constituents.
Yeah, that would be great. We are looking at not just flow and that sort of stuff. We're looking at in other the standards, turbidity, other things that are important for wildlife, water quality, etc. But if you can provide that info to Mark specifically, we're at the point we're writing our draft report right now. That's what I was on the phone with Mark on our speaking about today on one of our subchapters or appendices on modernizing the gauges. So we have all of those under our charge. And
that's great, Bill.
This is supposed to be the way to provide our state lawmakers with the information so that they can provide funding, and secondarily for our partners such as the USGS to have something to back up why they need more funding for things such as that.
Wonderful. Bill, it's great to know you're that contact, and it seems like this, as Loretta mentioned, this conversation is timely. We do know Mark well, and we'll be chatting with him. And we do need to switch gears to our final talk. Charlie, thank you so much for a great discussion.
Thank you. And
we'll switch gears to our final presentation by Tamara Kraus, Assessing and Forecasting Impacts of Wildfires on Drinking Water Quality. Tamara, it's all yours.
Hi, thanks. I'm going to continue on the thread that people before me have talked about, especially Charlie's discussion about effects of wildfire on water quality. And I'm focusing more on drinking water quality. But of course, the constituents of concern that we have in drinking water is also similar to the same concerns we have when we talk about irrigation water for agriculture, as well as recreation, fishing, boating, swimming, as well as ecosystem health and the constituents that end up in water that organisms are living in and drinking from. This is a slide just shows you a quick conceptual model. We've been talking a lot about sort of the catchment area processes and delivery of water and nutrients into receiving water bodies. And from drinking water treatment plant perspective, some of the constituents that are of primary concern are, of course, sediment and the turbidity that ends up in water that has to be removed during drinking water treatment. There's also organic carbon that reacts during disinfection to form chlorinated and brominated disinfection byproducts that are regulated by the EPA. So drinking water treatment plants have to ensure those don't exceed drinking water regulations. Nutrients aren't necessarily a direct concern because the concentrations aren't typically high enough to have a direct impact on drinking water quality, but of course they lead to the proliferation of phytoplankton, eutrophication, and dissolved oxygen issues, but also a growing concern across the state and the nation and the world is really the harmful algal blooms that grow that produce cyanotoxins, which are not good for drinking water, either in drinking water treatment plants or animals, pets, or humans that drink from water. There can also be, due to higher nutrient concentrations, issues with taste and odors that lead to a lot of complaints from people drinking water. I won't really talk about specific conductance, hardness, and alkalinity, but just generally those wildfire can also lead to changes in those constituents that can affect drinking water treatment plant as well as the transport through pipes and households. And then as Charlie pointed out, of course, we have to be concerned about contaminants, especially when wildfires take out urban areas, and Charlie touched upon that. Next slide. So quickly, why are fire impacts concern for drinking water treatment? It certainly affects treatment processes. It can, first of all, change the timing and duration of water supply because of the changes to runoff. It can have impacts on water quality and health concerns, and it can increase costs for water treatment. Some examples are, of course, sedimentation and reservoirs, as Charlie mentioned, that can actually reduce reservoir capacity, but also sedimentation within the drinking water treatment plants themselves in their settling basins. There can be much higher costs associated with coagulation. The coagulants are added by the drinking water treatment plants to remove turbidity and dissolved organic matter prior to treatment, can affect their filtration systems to make sure they meet disinfection byproduct regulations. Sometimes drinking water treatment plants actually have to turn to purchasing cleaner water from other sources if that's an option. And of course, the production of cyanotoxins and taste and odors is something that reservoir managers and drinking water treatment plants are concerned with. Just quickly want to point out that there's, of course, different spatial and temporal scales that fires can impact different systems that have to be considered. So, of course, rivers can be immediately impacted over the short term by fires that take out vegetation right around them. Reservoirs maybe are more integrated because they're receiving water over a longer period of time. And depending on what constituent we're talking about, the effects can either be immediate during the first storm surge, can even ash can even deposit nutrients into some water bodies, and other constituents might be entering the water system over much longer periods of time. Next slide. And I'm just going to quickly mention that because of the effects that vegetation, soil properties, geomorphology, interacting with fire affects water delivery, that in a lot of cases we not only have to monitor constituent concentrations, but we also have to measure discharge so we can look over time to understand how loads of these constituents have changed. And that, again, load is you get by multiplying a concentration by a flow or volume of water. And so it's important, as we talked about just prior to this, we have a lot of gauging stations around the state, but not only do we have to ask what stations are where and how often are they collecting data, but we also have to ask what are they measuring, because some stations are really just measuring flow. Others have the capacity to measure flow and constituent concentrations as well. Next slide. So I think everyone on this call is very aware that one of the huge strengths of the USGS is our data collection capabilities. We have a very large skilled set of technicians and field staff and researchers that are focused, focused on collecting data. I won't go through all of these parameters. Of course, we can go out and fill bottles and bags with samples. But one of the really key strengths that we have is the establishment of in situ sensors, not just for flow, temperature, pH, conductance, and turbidity, and those basic parameters, but also we have a lot of experience putting out specialized sensors that can measure things like chlorophyll, dissolved oxygen, nutrients, particle size, particle quality, all kinds of things that we're really always looking to test new instruments that can get us much more bang for our buck at these stations once they're established. Of course, there is additional cost with every additional parameter that you want to add to a station. So I just thought I'd mention that since someone was asking about station costs. It really does depend on what you're deploying at a station. One of the things our group is particularly excited about is that over the last couple of years, not only can we take all these instruments out to a fixed station that we can then collect temporally dense data at, but we also have loaded up as many instruments as we can onto our boats, and then we drive around, flow through water through them, and collect very spatially dense data. We've done this in some reservoirs such as San Luis Reservoir and Oroville, but we also do that in the Delta. Next slide. And I know that I'm gonna go a little bit long on time. I apologize for that, but I'll get through what I can. So on the left here, you can see that we have some temporally rich data. This is a station on Freeport on the Sac River, just above Freeport. This is kind of a very important site because it shows us what the water quality is coming into the Delta, which provides water to over 25 million Californians. And with the recent Calder fire, it will be interesting to keep tracking constituent concentrations at the station on the Sac River, which just upstream receives water from the American River that was particularly impacted by the Calder fire. And so you can see that you get very different types of data by putting an instrument at a single station and tracking it over time versus our boat-based data that gives us kind of a map of what water quality looks like, in this case of the Delta, over several years and seasons. Next slide.
Tamara, you've got about 2 minutes left.
Okay, I'll cut. I think 3 key slides, so let's see what I can get through. A lot of people have talked about remote sensing, and I just want to shout out to the capabilities we have to use remote sensing to look at not just turbidity and organic matter, but in particular to understand chlorophyll and cyanotoxin, harmful algal blooms that have the potential to produce cyanotoxins. And not only are we using hyperspectral data from satellites, but there's also a lot of efforts with our colleagues up in Oregon to try and get some drone multispectral sensor data off of drones, because we also know that cyanobacteria grow on rocks in rivers and streams. And the other importance is that there is a lot of satellite data, but there's a great need to ground truth the data by going out and actually collecting samples to make sure that the interpretation of the remote sensing data is correct. Next slide. Charlie made a shout out to our capabilities. We have kind of a long history in our group of doing research on dissolved organic matter, both quantity and composition. This is, again, important from a drinking water perspective. And it is known that post-fire, you see higher concentrations not only of dissolved organic carbon, but of the pool of the organic matter that is going to form trihalomethanes and haloacetic acids upon chlorination. So we've done studies to look at basically getting a fingerprint of dissolved organic matter to understand where it's coming from and how treatable it is. And we currently are analyzing samples from post-fire sites that Charlie mentioned, as well as we have been working with some colleagues in Oregon who are collecting samples at sites that we studied pre-fire to see how that dissolved organic carbon concentration composition is changing post-fire. Next slide. And then the last thing I wanted to talk about is something that I put in the comment, is that we have a group that's really working very hard to improve access to USGS data. We call this data integration, visualization, and access. There's a lot of work behind the scenes that goes to that. For any of you that have tried to pull data together, these people have to have a lot of expertise, but then they also have to understand the science and the goals and what data they're trying to pull together. And so the idea is not just to form these integrated data sets and basically host this on the cloud, but then to work with all kinds of agency people to figure out what kind of dashboards will be useful. And next slide is the last one, just to show you this is a work in progress. This is a USGS, a site that's intended to help us assess what gauges are actually physically threatened by fire. So on the left hand, the user can enter like a distance. In this case, it's 3 miles, and then it literally tells you, if you're a center director, you can hover over these points and figure out which of your stations are potentially about to be threatened or taken out by a wildfire. And
Tamara,
again,
we probably ought to wrap up to make sure you get some questions.
Okay. And I just want to say this links to things like the InsaWeb, and just to relate it back to Loretta's comment, is this is kind of the way that we can integrate with any other data portals that are being created. And that was it. There's one final, anyway, we can leave this up, or this one.
Thank you so much.
Thanks,
and I don't know if someone can post to the chat that link to Tableau so people can access that. It was on the slide, but it might be nice for people to see that in the chat. That would be helpful. I don't know if someone has that handy.
I actually put it up already, but I can.
Oh, you did already? Great. Thank you. So who's got questions for Tamara? She covered a lot there. Looks like Jim Falter.
Thanks for the talk, Tamara. I just noticed on one of your slides you had a picture showing that you could predict chlorophyll from hyperspectral imagery using AI. I'm wondering, have you thought about using that same hyperspectral imagery to get at the composition of the phytoplankton in the water?
The short answer to that is yes, although I am not the actual person that does it. We have Keith on the line if he wants to jump in, but but yes, as a matter of fact, that is particularly helpful and to be tuned to detect cyanobacteria, and that is one of the main uses. Is not only to pick up total chlorophyll, to pick up also the specific signal from the harmful algae. I don't know if Keith wants to add anything if he's on the line.
Sure. Hi, Tamara. Hi, everyone. My name is Keith Bouma-Gregson. I work with Tamara in the California Water Science Center, and my background is in harmful algal blooms. And yes, exactly what you said, Tamara. That is an interest in ours. There's actually a separate group at USGS that has gotten funding to explore that, and they've been collecting ground data, and also there's a hyperspectral camera on the International Space Station. And they have been working on looking at the bloom composition and how that changes the spectral signature.
Thanks, Keith. Does that answer your question there, Jim?
Yeah, thank you. I appreciate it.
Sure. Loretta.
I just wanted to verify, you said Chuck is the contact for our colleagues building the Forest Data Hub for the state of California. Is that right? Is that the person, or would it be you, or?
Yeah, I mean, Anka suggested that she could maybe recommend some other people, but Chuck Hansen, I gave you his email. Yeah, he's the one that really is leading what we call our data team, the folks that really can talk, the language of APIs and really understand what data they can pull into the data set and serve via our cloud-hosted database. And then we're using Tableau to make those dashboards. that I put the link in there that has in the chat that has links to a couple of different portals that we've designed over the last year or two. And we're really excited about this new capability that we've been developing. And of course, the more you build the database, the more valuable it becomes. So
I'll just chime in real quick. Chuck is a great place to start, and he's right here in Sacramento for that matter, in our center. But we will follow up and send you some additional people too in different centers and at the national level if you're interested in that.
Yeah, my colleagues with CAL FIRE and Air Resources Board and U.S. Forest Service are just initiating this effort. We don't want to reinvent the wheel, where we can learn from your engagement to date and all of that. Thank you.
Thanks for the question, Loretta. Does anyone else? Go ahead. Okay. Does anyone else have a question for Tamara? Questions, comments? I have a question for you. We've been talking about wildfires and their impact to water quality, and looking at some of your material, what are some strategies to minimize the impacts of fires to water quality? You mentioned coagulation. What is that, and can that work on a large scale?
So coagulation is really, these metal-based compounds like aluminum hydroxide, iron sulfate, things like that is actually added in drinking water treatment plants, and they have a charge on them, and so that's what basically they end up forming these larger flocks with sediment and organic matter and pull it out of the water. Obviously, people don't like drinking water that has a color to it or has sediment in it, even if it isn't bad for you. So that's a big job of drinking water treatment plants. And then they also disinfect to make sure there's not any bacteria that's harmful to people. And so as far as using coagulation at a much larger scale, there are actually quite a few studies that have looked at the use of applying coagulants to lakes and reservoirs to remove, in particular, phosphate, which is particularly amenable to removal by different kinds of coagulants. And there are some like whole lake coagulant additions for phosphate removal that have been shown to be effective at reducing phytoplankton and potentially thus mitigating the chances of forming harmful algae. And this is kind of, if anyone's interested in this slide, just a brainstorming list of like what you could do. I know a lot of drinking water treatment plants actually have people on their staff that are in charge of watershed management and looking at best management practices to protect their watershed to ensure high quality drinking water. And so a lot of those drinking water treatment plants sometimes do hire the USGS to do research to understand what the greatest threats are to their drinking water resources. And one example is that by putting in a gauge above the source water intake that measures in situ fluorescence of dissolved organic matter, they can even decide to turn off their wastewater treatment plant during a storm event that maybe is bringing in water that they can predict is going to be problematic and not even bring it into the treatment plant during that time.
Interesting. Thank you so much, Tamara. This has been a huge education. I think we could talk for hours on all these topics, but we do have to wrap up. So with that, I will thank everyone for your participation today. Again, I want to thank Alicia Torregrosa for taking care of the logistics of this meeting, as with the other two. Thanks to all the presenters for all the hard work you put into this. We've recorded this and the other two workshop sessions and hope to send those links out soon. So, I don't know about the rest of you, but this workshop has really been a refreshing change of pace from the day-to-day work life I've been experiencing here in the back bedroom of my house. This pandemic we've all been dealing with has really diminished our ability to meet face-to-face with our partners, and this workshop has given us a chance to sit down with you all and discuss what we've been working on, which is really the reason why we're here. And we're grateful to have this opportunity to connect with you, discuss techniques and data that you might apply to your management decisions. And I really hope we've been able to build a lasting bridge through these discussions. And I hope the conversation doesn't end here. We want our science to be useful and applicable to your decisions. And as managers dealing with our wildfire needs in this state, we really have the utmost respect for you and the role you fulfill. Finally, I really want to thank Loretta Moreno for her persistence in making this happen. It's been a rewarding workshop series. And with that, Loretta, is there anything you'd like to say in closing?
Just a wholehearted thank you to the whole USGS team for all the time that it took to pull this together. And I just hope that all the colleagues that have been attending do reach out to your scientists and follow up as they wish. And I just look forward to all the collaboration to come. It's really been eye-opening. I had no clue exactly the extent to which USGS is working in this space. So I think it's just been helpful to all the state to get a better understanding of applications and tools available to us. So thank you again.
Wonderful, our pleasure. All right, everyone, have a great rest of the week. Take care.